So in addition to the first law of thermodynamics, there's going to be two more laws that we're going to look at. The next one that we're going to look at is the second law of thermodynamics. And the second law says the following. It says that in any spontaneous process, there is always an increase in the entropy of the universe. So we can kind of write an equation for the entropy in the universe. And basically, what the entropy of the universe is, or the delta S of the universe, is going to be defined as the delta S of a system plus the delta S of the surroundings. As chemists, when we're looking at different, things to analyze, we get to define what our system is and what the surroundings are. The system could be this eraser right here. That would mean the surroundings is everything else in the entire universe. Our system could be this classroom right here. And then everything else would make up the entire universe. Our system could be the Ohio State University, and the surroundings could be everything else. But typically when we're doing a chemical reaction, we want to try to isolate our system and the surroundings, and we use an instrument called a calorimeter. If any of you took Chemistry 122 here at Ohio State, the very first lab that you did took this coffee cup and you put a thermometer in there and you dumped various metals in there, or you looked at a neutralization reaction, and you looked at how the heat released corresponded to the energy of a particular reaction. Okay? We made an assumption that there are no heat loss by the calorimeter to the surroundings. Okay? In most cases, if we're doing a more in-depth chemical experiment, we use something called a bomb calorimeter, which helps isolate the system and surroundings a little bit better than that coffee cup did. Okay? So when we analyze chemical reactions, typically we look at our reaction happening inside a calorimeter, and then that's going to be our system, and we can look at the heat transfer from the system to the surroundings. A couple of things that we want to look at from this equation right here is that if our delta S of the universe is positive, this is going to tell us that our particular reaction is going to be spontaneous. If the delta S of the universe is negative, then we can say our reaction is not spontaneous, or that the reverse reaction is spontaneous. If our delta S is equal to 0, we can say that we're at equilibrium. So the question is, how can we go from this broad statement here that's talking about the delta S of the universe in terms of system and surroundings, and how can we analyze different data that we might already know? Back in chapter 5, we talked about various chemical reactions, and we defined them as being endothermic or exothermic. So in an exothermic process, we're going to release heat to our surroundings, and how does that correspond to this delta S value? And are delta H and delta S related? So if we look in depth a little bit more at the delta S of the surroundings, we can compare these two processes. So let's look at an exothermic reaction. We know that an exothermic reaction is going to release heat to the surroundings. So that means our delta S of the surroundings is going to increase. Because if we release heat to the surroundings themselves, if there are molecules out there, will move a little bit faster, and that's going to increase that entropy. So most exothermic reactions have a positive delta S of the surroundings. If we compare this to an endothermic reaction, in an endothermic reaction, our heat is going to be absorbed by the surroundings. So if we're absorbing heat from the surroundings, our delta S of the surroundings is going to be a negative value. So from this data that chemists collected, we can come up with a relationship between heat and the delta S of the surroundings. So from these particular observations, we can say that the delta S of the surroundings is going to be equal to negative Q divided by T. And you'll see this equation written in chapter 19 of your textbook. Thermochemistry is a branch of chemistry called physical chemistry. And physical chemists like to take a lot of integrals and a lot of math equations and manipulate them around. Okay? If you liked geometry proofs and math proofs and that kind of stuff, you would love physical chemistry, because you're doing all that stuff, except it's with more bulked up, fancier mathematics, and typically with integrals and all that kind of stuff. If you make certain approximations, you can get different relationships. So in all cases, the delta S of the surroundings is going to equal negative Q divided by T. But typically, we like to make approximations that are more similar to what we observe in the lab. So if we observe a constant pressure, so at constant pressure, our Q is going to equal the delta H. So at constant pressure, we can say that the delta S of the surroundings is going to equal negative delta H divided by T. And this might not make sense about why we're doing this now, but a little bit later in lecture, we're going to try to define when a particular system is spontaneous and when it's not spontaneous, and we're going to need the information from this particular equation right here. So at constant pressure, the delta S of the surroundings is going to equal negative delta H divided by T. Okay? One thing that we can definitely say about the delta S of the surroundings is the following. It's the magnitude of delta S of the surroundings depends on the temperature at which heat is transformed. So depending upon how drastic this case is for delta S, it's going to depend on the temperature. Okay, so keep that in the back of your mind as we go through some of these instances and circumstances where we look at changes in entropy. One of the things is you're going to see these charts that are given in a particular textbook, because we want to try to figure out and be able to predict when our delta S of the universe is going to be positive or negative. Because we know that if the delta S of the universe is going to be positive, or if it's increasing, we're going to have a spontaneous process. So ultimately, everything has been put together right now, and we're trying to figure out when exactly can we predict if a particular reaction is going to be spontaneous. Okay? So we can look at different values of delta S of our system, and we also have to take into account the delta S of the surroundings. Because if we know the signs of these, we can figure out what the sign of the delta S of the universe is. Remember, the delta S of the universe is going to equal the delta S of the system plus the delta S of the surroundings. So if we have an instance where both of these are positive, that means our delta S of the universe is going to be positive, And at all temperatures, this is going to be spontaneous. If our delta S of the system is negative and the delta S of the surroundings are negative, that means the delta S of the universe is going to be negative. So under all circumstances, this is going to be not spontaneous. Those two are fairly straightforward. But what happens when we have a positive delta S of the system and a negative delta S of the surroundings? Or we could have an instance where we have a negative delta S of the system and a positive delta S of the surroundings. In each of these cases, we need a little bit more information before we can figure out what the delta S of the universe is going to be. So in each of these cases right here, these are going to be temperature dependent. Okay? And the driving force is going to be the delta H of the particular reaction. So in terms of trying to figure out what we need to know about a spontaneous process, in some cases we can predict just using the signs of the delta S whether or not a reaction is spontaneous or not. And in other cases we need some more information.